At this point, I think we've established some Karnaugh map essentials and how Boolean logic functions can be represented on a Karnaugh map. So at this point, what I want to do is get more into the formal definitions and terms and things that we need to actually apply Karnaugh maps to minimizing Boolean expressions. So that is the overall goal. So I note that here. The goal is minimization. And to do minimizations, you actually have to define what that is and some terms that support that. So let me just go ahead and start with minimization. We want to rewrite a logic function f into a minimal sum of products form. So minimal in this case means the fewest product terms. We understand what a product term is with SOP. And then we also want the fewest total literals. Well, we need to define what literal means. And then if we go through this process and learn these terms, we'll be able to go ahead and apply the minimization and read the Boolean logic function straight off of a Karnaugh map. Okay, so let's get set up with the terms that we'll need. First of all, we need to know what a literal is, and then we'll go through this list of product term, don't cares, that'll be a new thing, implicants, prime implicants, and essential prime implicants. When we go through this setup, at the end, we're just identifying essential prime implicants, and that turns out to be the minimization. All right, so let's get started. So first of all, let's talk about a literal. We have variables in the Boolean expression. I've had this set up with A, B, C, and D. Of course, it could be other variable names. But the literal is if you take a single variable and include both the variable and its complement, that is a literal. So this gives us a way of counting what things are used in a minimization problem. So we have literals. A product term is where you take two literals and you and them together. Okay, so here is an example of a product term BC, and you see how this shows up on a Karnaugh map. We've talked about that before. There is an edge case where it's still a product term technically, even if you only have one variable. So a lone literal is technically a product term. In this particular Karnaugh map, we'll see that this turns out, this big group of 8 turns out to be the region for variable D. All right, so if you look at the code here, this is CD. So where D is equal to 1, that's this whole region. That's still a product term. It's just an edge case of a product term. Okay, so let's move on. One thing that I'm not sure that we've discussed yet, but it depends on the order of topics that we talk about in class, but you need to know what a don't care is in order to fully understand the way that we do Karnaugh map minimizations. So it turns out there are some types of physical problems where there are certain input combinations that perhaps can't happen. And if that input can't happen, it doesn't make sense to specify what the output would be. Or it might be that these input combinations can happen, but we just don't really care what the output would be for those combinations. It might not be relevant for our particular problem at hand. This is abstracted at this point while we're talking about it. You'll see examples of don't care conditions as we work through examples in the course. Okay, so for now, let's just take it as a special kind of input. We don't know or we don't care whether it's treated as a 0 or a 1, which means it gives us an option. We can either include it to make a bigger group, or if we don't need it, we can just don't include it. All right, so in most textbooks, the convention for don't cares is to put an X onto the Karnaugh map. Sometimes you'll see a D, a lowercase d, or an uppercase D, D for don't care. Okay, so in a way, the name is, we care. It's just that we don't care what the output would be because it doesn't matter. All right, so we need to handle don't cares correctly. Use them if we need them, exclude them if we don't. That's the tip that you need to do the full implementation of minimization for Karnaugh maps. Okay, so the next thing that we need to know is what it means to have an implicant. A product term implies F if it's consistent, to be a 1 where F is equal to a 1. So I've got this Karnaugh map, all right, that represents the Boolean function F. This is an implicant because I've grouped these two things together. This is a region on the Karnaugh map, A bar, B bar, D. All right, and it's consistent with the Karnaugh map definition, or with a functional definition. So for example, I couldn't include M12 and M13 to be an implicant because 12 is a 0 and 13 is a 1. So while this is a valid product term, it's not implying F. It's inconsistent with F. So grouping 12 and 13 together would not be an implicant, whereas grouping 1 and 3 together is an implicant. Okay, so that's what an implicant is. The thing is, this is not the biggest implicant that I can have to include M1. So that's why we start talking about prime implicants. A prime implicant is an implicant that cannot be any bigger. All right, so you make the implicant as big as possible, and it becomes a prime implicant. So before, let me go back, we just had these two terms grouped together. But if I wanted to include M1 and find the prime implicant that covers M1, I actually see that the biggest grouping, all right, the grouping of adjacent cells that gives me the biggest groups need to be powers of 2, sizes 2, 4, 8. This is the biggest grouping for the M1 implicant. So that's the prime implicant here. In this particular map, I'm showing the prime implicants. All right, so I have this as a prime implicant that covers M14. All right, that's the reason it's needed here. And then this would be a prime implicant, and it covers 14 and 6, but those are don't cares, and so it's a little tricky on that, but we'll move through and go to the next case. Okay, so an essential prime implicant is a prime implicant that you can't remove it, all right, and still cover everything in F. Okay, so let me read this again. A prime implicant that is the only prime implicant covering an on cell, a distinguished one, it must appear in every minimal solution. So we have to include prime implicants in order to represent the minimal function. All right, so essentially at the end, what you do is you identify the prime implicants, and that gives you the minimized logic expression. So in this particular example, the only way that we can cover this M1 cell is to include the prime implicant that's this big group of 8. All right, we can't drop that, or if we did drop it, M1 would not be covered. The same thing occurs with M14. I have this prime implicant, all right, it's the group of 4 is the biggest one that covers M14. We got there by having the don't care. If we didn't have the don't care in there, that wouldn't have been a prime implicant. It would have been smaller. It would have been just 14 and 15. All right, so this is covered. All right, so it's a prime implicant because that's the only way to cover 14. Okay, so notice the part in purple. All right, it's not essential because if we drop that, we still cover the 2 1s that are inside the A bar B region that's shown with the purple dashed line. So we don't need that. It's not part of the minimal solution. And so that's part of the process that we go through. We identify the prime implicants and then keep the ones that are essential. And at the end, that gives us the final answer. So you can think of this as nested. All right, we have product terms. You could list all the different product terms, but then you have to identify what are implicants, what groupings would be consistent with representing the function F. And then you try to identify the biggest groupings, find the prime implicants, Once you find the prime implicants, you identify the ones that you can't drop. You need to cover all the ones and make sure you don't circle any of the zeros, and you're left with the list of essential prime implicants, which gives you the minimization. Okay, so in this particular case, when we go through this process, we identify the prime implicants, we identify that the purple part, which now I'm showing in red, is not essential, and so this term is minimized, or this Karnaugh map is minimized with the expression f is equal to d or b bar c. Okay, so we have two product terms. Remember, the d by itself is still a product term. D ended with 1 is a product term. All right, and so we have two product terms and three literals giving us this minimization for f.